Okay, so what we want to look at in this next part of this section is applications of the first and second derivative. What they are going to give you is an equation. So if an object is thrown straight up from an initial height of s of o feet with an initial velocity of v sub o feet per second, then the height s above the ground in feet after t seconds is given by the following equation. So this is an important equation that we need to know. They are going to say distance is s, which is going to refer to your height, is equal to negative 16 t squared plus v sub o t plus s sub o. And they're going to tell you, I can just jot down what they are, but s is equal to your distance or your height. T is just going to refer to time, and in this case it's going to be in seconds. V sub O is going to be the initial, and sometimes if you think of the O as original or the starting point, so it's the initial velocity, and S sub O is going to be the original or the initial height, the height above the ground. I better put this down. This is in seconds, this is in feet, this would be in something like feet per second. And it will be in feet because you're looking at 16. If you change it to meters per second, you would have a little bit different equation as you're looking at it. So then S sub O, as I mentioned, is the initial height. And that will be in feet. So we have this equation, and what we are looking at when we are talking about differential calculus, it's using a lot of calculus to help you predict or describe motion, and that's what we're dealing with in this particular problem. So S is just going to be distance. If you look at a distance versus time graph, think of this as y equals negative 16x squared, something like that. Your t is your x value, so it's going to be time is going to be along the x-axis, or is the independent value, and your height is going to be your, the height would be your y value or the dependent value. And if we were to look at some graph that deals with that, I'm only looking at half of this parabola here. It's a negative, so it actually turned down if I refer to this problem right here, but I already drew it going upwards. But what I want to point out is that, remember, if you take the derivative, what you are looking for is the whole thing we've been writing on that derivative page is it means slope. It's the slope of a tangent line to the curve at any point on the curve. So the first derivative is referring to your slope, and if you look at the units that you are dealing with for this particular problem, it's the change in y over the change in x. The y-axis is in feet, and the x-axis is in seconds. That means that the first derivative is actually referring to velocity. So the first derivative, if you say the first derivative, that's the same thing as velocity. And I'm running out of room on my paper here. So it's just v of t. Now if you were to take that particular problem, and what happens if I do the second derivative? Well, here we have velocity, which is in feet per second, and we're going to compare that to time. So if I take the first derivative of velocity and I look at that graph, sorry about that, slide that up, your units are going to be the change in y over the change in x, which is feet per second, and that's something that they look at as feet per second squared. And if you remember from science class, that means the same thing as acceleration. So the second derivative is going to, and then I start writing and I put T. So the second derivative of distance means acceleration. So you could look at it like this. The second derivative, which is actually the first derivative of velocity, is going to give you the acceleration, which is the change in velocity with respect to time. So the first derivative is velocity, and that is the change in distance with respect to time. And the second derivative of distance, which is acceleration, is the change in velocity with respect to time. So you have the change in distance with respect to time, and you have the change in velocity with respect to time, which gives you velocity and acceleration. So that's what the two equations are talking about. So let's look at an example of how we can actually apply that information. So we have this example here. Let me slide it down. Hopefully you can read it. Forget about that stuff I have written at the top there. And it's not all going to fit in there. Suppose that a baseball was thrown upward from the roof of a building at 192 feet high and an initial velocity of 64 feet. Part A says what was its velocity at t equals 1 and at t equals 5. So we start out and let's draw a picture of what's going on. There's a whole bunch of questions here that they are going to have you answer, and I'm going to try to keep the question there, but then put the answers A, B, C, D, E, and F below it so you can still read the original problem. But this example is what we're going to be working with. So it says, suppose that a baseball is thrown upward from the roof of a building. So we know that this height here is 192 feet. That's the height of your building. And you're going to take this ball and you're going to throw it up in the air, and it's going to come back down and it's going to hit the ground. So the ball is thrown upward from the roof of a building 192 feet high, and its initial velocity is 64. So remember, initial velocity was v sub o, and we know that that is 64 feet per second. So we had that equation that I had given you that I said was going to be of importance. And if we want to find A, what is the velocity? Well, we know that velocity is going to be the derivative of distance. So the S equation was this. S is equal to negative 16t squared plus v sub ot, which stands for initial velocity times the time, plus S of o, which is the original height. So I can come up with a distance equation given this example that we have. And based off of that example that we have, we know that 192 feet high is the same thing as S of O, that's the original height. And then it says that the initial velocity is 64 feet per second. That's going to be v sub O. So if we substitute that into this equation, we are going to get something that looks like this. 64t plus the original height, which is 192. Now what is in red means that this equation, S is equal to negative 16t plus 64t plus 192, is specific for just this particular problem, because those are pieces of information that are given to us for this problem. So what we need to do is we need to go ahead and find out part A, which is what is the velocity at t equals 5 and t equals 1. So what we know is that velocity is the same thing as the first derivative of distance. So I need to take the derivative of S is equal to negative 16t squared plus 64t plus 192. So if I take that derivative, you get negative 32t plus 64. That is your velocity equation, and they want to know what is the velocity after 1 second. So you get negative 32 times 1 plus 64. And that tells you that the velocity after 1 second is going to be 32 feet per second. Now that makes sense. And where is your ball at this point in time? Well, your ball, we know that as the ball travels upward, it slows down due to gravity. So the ball takes off at 64 and it's still going 32, which is going to be that upward direction. Your negative velocity is going to be slowing it down, and that's where you get the negative 16 from. It's the acceleration due to gravity is negative 16 feet per second squared. So if you're dealing with meters per second, you would have something different here. So it's slowing it down, so your ball is still somewhere between the height and the initial spot that we threw it from, which is that height of 192 feet. Now they want to know what is the velocity after 5 seconds. So if you put in 5, oh, and I started to put it right there. So if you put in 5, you get negative 32 times 5 plus 64. And if you were to go ahead and calculate that, I believe that you would find out that that's going to be the velocity after 5 seconds is going to be negative 96 feet per second. Now the negative just is referring to direction, so I know that for part B, my ball has to be somewhere over here where the parabola has started to turn downward. So the ball is falling down after 5 seconds. It reached its peak somewhere between 1 and 5 seconds. Okay, let's see, I'm at 11 minutes right now, almost 12. I think I'm going to go ahead and stop this, and I will start another video just because I have to keep these 15 minutes long. So hopefully this explains a little bit about the velocity for this particular problem.